Great. Anybody have any homework questions? All right for now. 17 on particle kinematics. Do you have it with you? Anybody? Okay, so particle kinematics. '17. So it's a bicycle moving with a constant speed of 8.8 meters per second. Okay, so it's going 8.80 meters per second, which means that the two axles of the wheels, the centers of the two wheels, are going 8.8 meters per second. Each wheel has a radius of 0.34 meters. And you can think of like the definition of not slipping is that the part of the wheel that's in contact with the ground has no velocity relative to the ground. That would be slipping. And it also has no parallel acceleration, relative to the ground. So it would be slipping if it had a velocity that the ground didn't have, and it would also be slipping if it had a acceleration in this direction that the ground doesn't have. Okay, it does have, that point of the wheel does have a centripetal acceleration, but it doesn't have an acceleration parallel to the ground. Okay, so yes, yep. So the point, and actually I didn't go into this year the derivation of the rolling without slipping equations, but those are the assumptions that you use to derive those equations. So in rolling without slipping in general. The velocity is 0 of that point. And second, the part of the acceleration that's parallel to the ground is 0. And we want to calculate, so let's call this point A. We want to calculate the velocity of that point A. What's the velocity vector of a point on the bottom of the wheel? Well, that's sort of a funny question because I don't know who wrote these questions, but it says that we're assuming that point has 0 velocity, so let's skip that. Okay, how about acceleration of a point on the top of the wheel? And now this one, so let's say this, let's call this point B. I think this is actually C. And then D, what's the acceleration of a point on the bottom of the wheel? This is not 0. And then it asks for acceleration why not just, once you've calculated the velocity, because we have to do that first in this problem, and then just use the fact that acceleration is equal to the time derivative of the velocity. That's sort of a fundamental understanding problem, question. Okay, so
Is there going to be a difference in the acceleration other than the direction between top and bottom?
Yeah.
That doesn't make it super sense.
Yeah.
I mean, other than your coordinate system is, you can base it at the bottom.
Mm-hmm. Yeah. Well, we'll see why, but it has to do with relative motion. Okay, so to calculate the velocity, so we know that the velocity of the point A relative to the ground is equal to, so let's call this the center, C. It's equal to the velocity of A relative to the center plus the velocity of the center relative to the ground. The velocity of A relative to the center, what that's saying is, what if we didn't know that the center was moving? Then that's just purely a circular motion question. That's saying, imagine that the center is fixed. What's the velocity of that point A? That's just like any circular motion problem. So this we're going to get using that the velocity is equal to omega cross r. Okay, so first, what about, so velocity of C relative to the ground? That's the one that's given. And that is, if I use a coordinate system like this, that's positive 8.800. And we know from the rolling without slipping equation that that's equal to negative omega r, 0. And so this says that 8.8 is equal to negative omega times 0.34. And so omega is equal to negative, what's 8.8 divided by 0.34? 25.88. And the units are radians per second.
And this is velocity in the x direction. So
yeah.
This is not a circular.
The velocity of the center is a regular velocity in meters per second in the x direction. Omega is an angular velocity. So that's going to be, so this is the z component of the angular velocity. Anytime you're doing a rotational motion, a circular motion problem in the xy plane, you're only going to have a z component for the angular acceleration, angular velocity too. So omega is equal to 0, negative 25.88. And now we have everything we need to use the relative motion equation. So the velocity of A relative to the ground is equal to the velocity of A relative to the center, which is 0, 0, negative 25.88, crossed with the R vector. The definition of that R vector is from the center of the circular motion to the point you care about. So that's going to be 0.34 in the negative y direction.
Wait, what? Are we doing 0.8?
0.8, yes. So 0, positive 0.34, 0. So yeah, the point we're looking at isn't B, it's A. So that R vector is 0.34 in the positive y direction. And if you take the cross product, you get 8.8. Sorry, let me make this equation right. So velocity of A relative to the ground is equal to velocity of A relative to the center. That's what this is. Plus the velocity of the center relative to the ground. That's 8.800. That was given. And so you get 17.6000 meters per second. So at the top of the wheel, a point at the top of the wheel is going twice as fast as the center of the wheel is going. Any questions about that one?
What was the acceleration? Was just it wouldn't said only the parallels, but then perpendicular does have a value.
The perpendicular does have a value because of centripetal acceleration, and I think that's the next thing we have to calculate anyways, acceleration of A. Okay, so this is part C. The acceleration of A relative to the ground is equal to the acceleration of A relative to the center plus the acceleration of the center relative to the ground. How are we going to calculate the acceleration of A relative to the center? Yeah, watermelon equation. So this is alpha cross R plus omega cross quantity omega cross R. And the acceleration of the center relative to the ground, well, this is moving with a constant velocity, so this is a zero vector. This comes from the rolling without slipping equations. It says this is equal to negative alpha R 0, 0. Alpha is 0, so that goes away. All right, so acceleration of A relative to the ground is equal to 0, 0, 0 crossed with, what's the R vector? We're looking for the point A again. Yep, in the Y. Yep, just like it was for velocity. Yep, so 0.340. So that part goes away. And then you have zero, zero, negative 25.88. That was the angular velocity we got before. crossed with the quantity 0, 0, negative 25.88, cross 0.340, and we already did that one in part A. So that comes out to be 8.8000. This is the tangential acceleration. Okay, no, because this is just sorry. This one is just omega cross r. And so that is just that first term there. And all this together is the centripetal acceleration. And so there's no tangential acceleration in this problem. What's 25.88 times 8.8? Okay, so that is in the y direction, and it's negative 227.74. Meters per second squared. No, because y always has to be the weird one. And if you think about what it means, since this is only centripetal acceleration and we're looking at that point at the top of the circular motion, it has to be down. So you can sort of sanity check your directions that way by just thinking of physically what these things mean. Okay. Yeah.
In the other problems where they give you an acceleration, rolling without slipping, is there something that's always is alpha sometimes?
Yeah, alpha can be non-zero if this was changing speeds, because you have your two rolling without slipping problems. Equations are that the velocity of the center is equal to negative omega r 0, 0, and the acceleration of the center is negative alpha r 0, 0. And so it's just a matter of whether you have acceleration, whether what the velocity is. All right, and then part D asks to calculate the acceleration of the point at the bottom. Anybody have a guess what the acceleration is going to be at the point on the bottom of the wheel? Yeah, the opposite, exactly. It's so since that term just comes from centripetal acceleration of the circular motion around the center of the wheel. If you go to the bottom, it's just going to be an upward acceleration of negative 227. But let's do that. Yeah, draw me a picture or something that looks convincing. Don't write that and then write 4 question marks and put a star by it like you need to come back to it. Show some confidence. Okay, so part D. So now we want the acceleration of the point B relative to the ground. That's equal to the acceleration of B relative to the center, plus the acceleration of the center relative to the ground. Again, this part is going to go away. This part comes from circular motion, so this is the watermelon equation. So the acceleration of B relative to the ground is equal to 0 crossed with, what's the R vector for the point B? Yep, 0, negative 0.340 plus 0, 0, negative 25.88 crossed with 0, 0, negative 25.88 crossed with the R vector of 0, negative 0.340. This one goes away. This one is negative 8.800. And then we'll cross that with 0, 0, negative 25. And you get negative positive, so 0, 227.740. And so the acceleration of B relative to the ground is that 0, 227.740 meters per second squared. Yes. It'll be 0, yeah, but you can calculate that the same way. So let's actually do it just to, now that I think about it. I mean, we know what it's going to be, but let's see how it works out, okay? So the velocity of the point B relative to the ground we know from the way rolling without slipping works that it has to be 0, but let's see it happen. So this is equal to the velocity of B relative to the center plus the velocity of the center relative to the ground. This is what's given, 8.8000. This one is omega cross R. So the velocity of B relative to the ground is equal to, omega was 0, 0, negative 25.88. The R vector is 0, negative 0.340. And we're adding that to 8.800. If you do this calculation, you get minus 8.800. And so add those two together and you get the 0 vector. Yep.
The velocity of the center relative to the ground, does that have your rolling without slipping equations built into it?
Yeah, I mean, that's how fast the center of the wheel is going. So that's how fast the bike is going. And that's what was given to start the problem. But yes, this is equal to, this is the one that we know is equal to negative omega R 0, 0. we don't need that in this case because it's what we were given in the problem. Like we used that initially to figure out what omega was. Okay, and the last question, E, is conceptual, and it says in parts A and B, we calculated VA and VB. Why can't we just take the time derivatives of these for the acceleration at A and the acceleration at B? So this is always an important thing. It's going to come up a lot in this class. What is it that lets you take the time derivative of a velocity and get the acceleration? Because that is the definition of acceleration. I mean, there's no denying that if you take a time derivative of velocity, it gives you acceleration. Yes, that's exactly right. These are instantaneous velocities. And what you need to be able to differentiate with respect to time is you need those velocities as functions of time, okay? And so we're going to do a lot of calculations in this class where you get instantaneous things. Those aren't functions, and that means you can't take those derivatives, okay? What changes is the R vector, by the way. So if you came up with the R vector as a function of time, you could actually set this up so you could take the time derivative and it would work out. But let's not do that. But yeah, like you said, just think of that. Like at every time you see a problem and you calculate a velocity or a position, ask yourself or make sure that you're clear. Did I just calculate an instantaneous position and or velocity, or did I calculate a position or velocity as a function of time? You have a lot different tools to work with if you have it as a function of time. Any other homework questions you want to see?
So why is the acceleration at the point relative to the ground?
Okay. So 18. This one, you have a ball rolling down an incline. It gives you the angle, but that actually doesn't come into this problem at all. You're given that the angular velocity is 20 radians per second. It's rolling down, so this is 20 radians per second. And gravity is making it speed up, so the angular acceleration is also going this way at 15 radians per second squared. Let's call that center. And all you have to do for this one is if you choose a coordinate system with the y-axis going straight out of the incline, what am I doing? This is y, this is x, okay? If you choose that coordinate system, then your omega is just equal to 0, 0, negative 20. your alpha is equal to 0, 0, negative 15. Those are just from the right-hand rule. And your R vector, which would be, you'd have to use cosine and sine if you didn't use this tilted coordinate system, is just, well, it depends on the point. So if I name these, let's call this A and this B, then your R vector for A would be, it says the radius is 0.05, so this would be 0, 0.05, 0, and our B would be 0, negative 0.05, 0. And then it also lets you use these equations that say the velocity of the center, that assumes relative to the ground, is negative omega r 0, 0. So that is negative of negative 20 times 0.05, 0, 0. And so that is 1, 0, 0.
Only assuming when you say velocity of c that's relative.
Yep. If that's not given explicitly, then it's always relative to the ground. And the acceleration of c is negative alpha r. So that's negative of negative 15 times 0.05, 0, 0. And so that is 0.75, 0, dang it, 0, 0. Yes? Oh, okay. I did make you do it in that funny axis. Okay, well, at that point, you could convert your answers, which would probably, I would do the calculation in the rotated axis and then convert. But to be honest, I would never ask you a question like that on a test anymore. That's kind of the way I used to teach this. So, so don't worry about that. But I did briefly go into rotation matrices earlier, right? So now if you want to go, so if you want to go from this coordinate system to this coordinate system, that's a rotation of positive 20 degrees about the z-axis. So the rotation matrix Q is cosine 20, sine 20, 0, negative sine 20, cosine 20, 0, 0, 0, 1. So that's 0.940, 0.342, 0, negative 0.342, 0.940, 0, 0, 0, 1. And then the velocity of C in that coordinate system is that rotation matrix times 1, 0, 0. Oh, I can do that. That's not hard. Well, yeah, so Q times 1, 0, 0. And so that is 0.940 negative 0.3420. And if you think physically about what that vector means, that makes sense. It's going mostly horizontal, but a little bit down. And the acceleration of C in that coordinate system is that rotation matrix times 0.7500. That one I can't do in my head, but there are a lot of cases where once you get used to rotation matrices, it's a lot easier to do the calculation in a funky coordinate system and then do the transformation than to try to go through the whole thing with sines and cosines and unit vectors and stuff. Yep. 160 degrees. No. 340 would work actually. And if that didn't work, check and see if your calculator's in radians. That's but 160 would not work. That's the exact opposite degree. Yeah. 340, no, 340 would not work. 380 would work. It's positive 20. 340 is negative 20. So what's important there is that you go from the coordinate system that you have the vectors in to the coordinate system you want. Okay. And if you do it the other way, like you were thinking, you go from the one you want to the one where you have the vectors, everything goes backwards. Okay. I got to calibrate my thing. Yeah, right.
Okay, so you multiply the velocity by the first row in the matrix?
I just did the matrix multiplication, but my vector only had an x component, so that's how it works out.
Oh,
yeah. Any other homework questions? Yep, that's right. Yeah, if it's just asking for the center, then all you need to use are the rolling without slipping equations. How about 21? Did that one go okay? Oh, so you did up to 20. Nope. Okay, let's see. All right, so we have this wheel. That's initially moving at 8 meters per second. And it has a diameter of 0.72, so what we care about is the radius, so that's 0.36 meters. And then we want it to stop over a distance of 10 meters. So what's the angular acceleration for the wheel to stop in 10 meters? Okay, so we can figure out the acceleration of the center that's required if this is C. So if we use this equation, 2a times p minus p0 is equal to v squared minus v0 squared. That's from physics 1. We get 2a times 10 is equal to 0 squared minus 8 squared. And so the acceleration of the center is 64 divided by 20 negative. So that is 3.2 meters per second squared. And now the acceleration of the center we know is equal to negative alpha r 0, 0. So negative 3.2 is equal to negative 0.36 alpha. And that says that alpha is equal to 8/9, which I think is 0.8 repeating. And it's positive.
What does the 2a stand for in physics?
That's just, so they're the three constant acceleration equations. So they're based on t is the elapsed time, p0 is the position when time is equal to 0, v0 is the velocity when time is equal to 0, p is the position at time t, v is the velocity, at time t, and a is the constant acceleration. And the three of these that I use are v equals v0 plus at, p equals p0 plus v0t plus 1/2 at squared, and 2 times a times the quantity p minus p0 is equal to v squared minus v0 squared. So for any like one-dimensional motion, those are helpful. There's also vector versions of those, but when you took physics 1, it's possible you use slightly different notation, but everybody in physics 1 did stuff like that. Okay, that's all. See you Wednesday.